Hey physics, welcome back. Today the screencast is going to be about wave speed and wave interference. So by now you guys are all well acquainted with different types of waves. We have both longitudinal waves and transverse waves, and I'm not going to draw a longitudinal wave here, but I am going to draw your typical transverse wave. And by now, you should all be very familiar with this. If I were to draw the distance between the middle of the wave and the crest of the wave, I would get the amplitude of the wave here. Additionally, I could also draw the distance between the trough and the middle, and that would also give me the amplitude. And you also know that any distance between two of the same parts on a wave is going to give you the wavelength, also called lambda. And I could take this wavelength here, and right now it's measuring the distance between two crests, but I could also move it between two troughs. As long as I pick two of the same points on the wave, then any distance is going to give me the wavelength right here. I can put it right here, but I'm going to put it between these two crests. Okay. So you also know that the wavelength is the time it takes a wave to move one full cycle, and I'm going to kind of demonstrate that right here. If we imagine one wave moving along the length of a rope, if we see it moving here, if you imagine this is moving through time, and we draw a little red line here, so this is T1. Actually, this is a little confusing. The rope is not getting longer. So T1 here, T2 here, and T3. As this wave moves down the length of the rope, it retains the same wavelength, as you can see right here. The wave has not changed size, the wavelength remains the same. But as it moves through time and travels down the rope, the time between when the wave is right here and when the wave is now right here is going to be the period. So one wavelength, the time it takes the wave to move one full wavelength, move one full cycle ahead, is the period. So I'm going to write that down here. Time to move one full lambda wavelength is equal to the period in seconds. Okay, great. So that's the relationship between wavelength and period. And now we're going to talk a little bit about wave speed, because although this wave is moving forward, actually, I'm going to explain it in a slightly different way. So today in lab, you guys were shaking slinkies, and you were actually measuring wave speed, and you saw that it didn't matter how vigorously you shook the rope. The wave traveled at the same speed down the length of the slinky, regardless of how hard or how frequently you shook the slinky. What mattered in the wave speed, to speed up the wave, you tightened the slinky. You changed the material property of the slinky. So, in fact, wave speed is not dependent on frequency. It's determined by the property of the material that the wave is moving through. So, imagine we have this wave here and this wave here. They could both have the same wave speed if they are the same material, but we see so wave speed is just dependent on the property of the material. And so these two waves, if they are the same material, they're going to have the same wave speed, and you can calculate the wave speed. Write that down here. Wave speed. It's equal to the frequency times the wavelength. Or lambda. And I guess the best way to imagine this is imagine you're a little person standing right here looking at this wave passing you by. If you were to count how long it took till the next wave crest right here passed by you going in this direction, that would give you the frequency of, if you were to calculate how many waves passed you by in 1 second. And then you were also to measure the distance between the heights of the waves, so distance times the frequency would give you the wave speed. So in real life, you're hearing the results of this this wave speed all the time. So sound waves that are passing through the air have different frequencies, but they also have different wavelengths from one another. So a low sound wave that has a low frequency but a large wavelength, and a high sound wave with a high frequency and a low wavelength. And a short wavelength, so high frequency, short wavelength. Both of those will have the same overall wave speed, which is why when we hear music or someone talking, both the low pitches and the high pitches travel to us in the same amount of time, and we hear them together. Okay, so that's it for wave speed and wavelength and our wave here, but we're going to move on and talk for a second about interference. So interference is when we have two or more waves coming together and interfering with one another and forming a new pattern. They form what's called an interference pattern. So imagine we have two waves. 1, 2. Okay, some simple math here. Two waves, if we add them together, we are going to get a wave that is twice as big. That's not so good. Try that one more time. Twice as big. Like so. The amplitude here is twice as big. So the wavelength, the overall wavelength here, lambda, doesn't change, but we see the amplitude here, amplitude is times 2. This is 1 here and 1 here. So the wavelength, overall wavelength doesn't change, but the amplitude is twice as big. So adding these two waves together gives us a wave with twice the amplitude. Now, a wave that looks like this added to a wave that looks like this is going to give us nothing. So both of these are types of interference patterns. We call this type constructive interference. We're constructing something, we're making it bigger. It's also called reinforcement. This type of interference pattern, when we see basically annihilation of the wave, is called destructive interference. Or cancellation. So let's go a little lower here. Let's imagine two waves traveling in different directions coming at each other. So these two waves are both moving in opposite directions coming at you. You can imagine these to be like ripples in a pond. If you throw two stones in a pond at the same time, the ripples will start to travel out away from the path, the part of the pond where the pebble dropped in, and they'll start to, in one direction, move towards each other. Now, if they move towards each other and you've timed it that in such a way that when they arrive together and they form a wave that's double the amplitude, so this would be an example of constructive interference. This is what we call, these waves have arrived in phase with one another. And so, again, we get a wave with 2 times the amplitude. Now, if these waves arrive in a way such that they result in a cancellation of the wave, we call this out of phase. And this results in a wave with 0 amplitude. This concept of interference patterns in phase and out of phase is going to be really important as we move into talking about standing waves over the next few days. So make sure you come to class with a solid understanding of this. Okay, so what we've covered today: interference patterns, constructive and destructive interference patterns, how waves that are arriving in phase result in constructive and waves that are arriving out of phase result in destructive, as well as the overall wave, what it means to have a wavelength, the time to move one full length ahead is equal to the period, and wave speed is not dependent on, it's dependent on the property of the material, and it can be found by given the frequency times the wavelength. Okay, that's it for today, and I will see you all in class tomorrow.